smoke! Just pretend the lasers happened. Right. So, quantum computing. It's just clever words, and the rest of it's going to be pictures of dogs. So I hope you're ready. What I actually plan to talk about is firstly I need to know what you know, because I want to know how careful I have to be, and are you going to think I'm an idiot? So I'll be so prepare yourselves for those questions in a second. Also be having a very quick overview of classical computing. I know we've got, I think, a mix of backgrounds in here, so how much you know about how classical computers work, I'm not sure. Then we'll have a look at the key principles of quantum mechanics, and therefore quantum computing, which are superposition and entanglement, and move on to wave theory, real-world applications, and then look at quantum supremacy, which some of you may have seen in the news recently. Google and IBM having a big tech giant fight-off, which is always fun. So first to open, what does quantum computing mean to you? What do you know about it? What kind of level? When did you first get introduced? I just want to get a feel for where you are. So any volunteers willing to help me out here?
Broken security.
Pardon, sorry?
Security. Yeah, broken security.
Yes, very much breaking all encryption very, very quickly, all across the board, scaring everyone, including Russia and China, which is exciting. Anything else? So any starting knowledge of what are kind of the fundamentals, or have I got a lovely clean slate in this room?
You've got a lovely clean slate.
Oh, my dreams!
You can pretty much just make it up.
Good. I'm going to change around my presentation right
I would
now.
declare I am a mathematician.
Ah, incredible. Well, lovely to have you in the room. If there is anything at any point that anyone wants to add, or if people want to interrupt me with a question, it's a weird subject, and I had a lot of trouble. It's kind of a circle of knowledge, and putting it together into something linear was very difficult. So it bounces around a little bit for me to try and build up these concepts. So if you get a bit lost, I may just say I will get there in a minute and try to explain it, or just be like, sorry, I'm just not very good at explaining. But I'll give it a go. So starting off with classical computing, so most of you will know the fundamental building blocks are 0 and 1s, so everything is broken down to binary, and this includes everything you see, like voice, video, everything gets broken down into these linear things. So binary is stored in two states of a transistor. It's either filled up with charge or it's got no charge. And everything that we see, everything that we compute, every algorithm is broken down to these 0 and 1s at this very, very basic level. You've got layers and layers of languages on top of that, so obviously if those of you that program, it's quite complex, that's broken down to machine code, that then goes all the way down to 0 and 1s. So the problem with classical computers is that however much we build them, however many more we add, there is still some physical limitations on what they can achieve. So you've got IBM's Summit supercomputer. It's absolutely massive. It can do huge calculations in very, very short amount of spaces of time, but it's got the physical limitations. Some things take days. The more we add complex problems, it's just taking longer and longer to achieve things that we want to know the answer to. So people started thinking outside the box and go, maybe instead of just improving these computers, making them smaller, making them faster, making them store more data, how else can we model problems? How else can we build something that solves these problems that we have? So we needed a bit of a rethink. There's many sets of problems that we need the answer to. I'm going to glaze over this really quickly, mainly because I don't completely understand it, and because it's quite boring. But we essentially have sets of problems that, given any size of input, you can solve quite quickly, and the amount of time it takes to solve grows quite polynomially, or it doesn't matter about that. Moving on. I'm going to lose my train of thought several times during this, so you're going to have to bear with me. But there are several problems that as you increase the size of the input, the amount of time it takes to solve the problem grows exponentially, and that's where we're running into problems. And also, once we've solved a problem, that's taken a supercomputer 2.5 days to complete, how do we then check that it actually has the correct answer? It gets very wishy-washy very fast, and we can't afford to be spending days running these algorithms over these computers. So we needed a better solution. So enter the qubit. So this is quite a big concept of quantum computing, so you're going to have to bear with the first bit of this. So a qubit, instead of having two states like a classical computer, it exists in either 1, 0, or in both at once. And it not only stores a combined value of 1 and 0, it actually exists across everything in between 0 and 1. So it actually represents a probability. This is a bit strange. So if you imagine, obviously your transistor is turned on or off, your qubit, you don't always know where it is. It can exist in 1, it can exist in 0, or it exists as both. And that can be anywhere along the scale of it's more likely to be 1, it's more likely to be 0. And if you think of how many bits are in a classical computer, and then you think of the complexity of every single one of those, having any number of probability of what they are, it starts to get a bit confusing, but very, very powerful if we can harness it properly. So qubits can actually take quite a lot of forms. It's kind of a name of a concept rather than an actual thing. So it can be represented by anything that displays the properties of superposition in quantum mechanics. So anything that can exist as one state, as its second state, and also as a mixture of those states. And there are quite a few things that can represent that. So the spin on an electron or the charge of a photon. We're going to mainly look at photons because electrons get confusing. So, one of the key principles of quantum computing is superposition. And superposition is actually the name for so when I'm talking about a qubit existing in both of these states, that is existing in superposition. When it's in this unknown and it hasn't settled on either 0 or 1, that is superposition. And you'll understand why there's a cat in a second. So who here knows about Schrödinger's cat? Good, lots of hands. So obviously it's quite a well-known experiment, and it's also a really good way to explain and also kind of the theory behind superposition. So Schrödinger had a cat. Do you know what, I feel like I've wiped from my memory whether he actually did this to a poor cat or not. Hopefully not. Didn't. Oh, goodness. It's fine, we can sleep at night and continue with the science. But it was kind of a concept of applying the quantum mechanics to everyday objects. So in his little box, Schrödinger put this theoretical cat, and he closed the box, and within this box he had a little particle that was decaying at a certain probability. And if a certain amount of decay was let off from this particle, it let go of a hammer, the hammer smashed the poison, and the cat got poisoned, and the cat would die. Quite an elaborate way to murder your ex-wife's cat, but if that's what you want, that's what you wanted. So the point behind this is that when the cat's in the box, they completely seal it off, and the idea was that no one outside the box knew whether this cat was dead or alive. And that's all down to this unknown probability of this decaying particle. And it's if you can't see something, and if you don't observe it, and if no one knows what the outcome of this cat experiment is the cat in one state, or is the cat both dead and alive at the same time? And this is kind of the idea behind superposition. So it's both! Spoiler! Yeah, pretty much said all that already. So quantum uses a lot of very dramatic and aggressive terms. So it's actually called collapsing into a state. So when they open that box and they're like, oh, Tiddles is dead, that cat has then collapsed. It was quite brutal, wasn't it? That cat has then collapsed into one state or the other. So they open the box and Tiddles is like, why did you put me in a room with a hammer, you crazy, crazy man? Or it's had a really bad day. But the point is that it's then in either 0 or 1, dead or alive. And until that, it's sitting in this probability in between. Right, so second key concept is entanglement. I'm going to be quite brief with this because it's quite hard to explain until I get further on, so you might have to bear with that a little bit. Was superposition, did that all make sense? Excellent.
So do you want to hold questions till the end? Or?
Hit me.
The probability that it's 0 and the probability that it's 1, do they
Yeah.
add up to 1 like I would hope?
Yes.
Mathematician says yes.
It's a probability distribution term, if that means anything to you.
Cool.
Yes, yes it is. There's the words I know better. I was like, I'm being very careful to not, I don't want to say anything that's wrong, so I'm hoping that everything I say is correct, and there's just going to be some things I'm like, I'm sorry, I just can't absorb that much knowledge at once.
But only when it collapses. Before then, it's both.
Yeah, so it's living in this state in between, and then we're on to entanglement. So, entanglement is an extremely strong correlation that exists between two quantum particles, and this is kind of a very wishy-washy definition, especially in the scientific world. People don't really know what it is yet, and there's all kind of observable things that will alter a particle in one part of the universe and an identical particle somewhere else in the universe across a great deal of space will match the manipulations you apply to one particle. And everyone's kind of going, oh, this is amazing, but how does it happen? I was like, shh, don't ask difficult questions. That's pretty much how the whole of quantum is going through it. So yeah, they're linked across space and distance, and it's the ability of separated objects to share a condition or state. So they kind of have this, it's like twins, one breaks their arm, the other one's like, oh, that hurt a little bit. It's something in them that they've got this kind of connection, and we haven't actually been able to detect what it is that has them together, but the fact that they are tied together is called entanglement. So once you've got more than one particle entangled, they can only ever be in superposition together. So you can't have, if I've got two particles, I'm a cat that's dead or alive, I'm the cat that's dead or alive, either they're both in that state, but as soon as one decides I'm dead, the other one then has to reveal its state as well. And this is how quantum computers basically string together, so one qubit wouldn't be very useful, like, yeah, I can be two states at once. How are you going to solve my math homework with that? But with entanglement, you can start bringing these qubits together, bringing these bits together, and start creating a massive amount of really powerful processing power and data storage, which is exciting. Yeah, so as I said, qubits work on these same principles, so same state until they're collapsed. Then their states are revealed, and that's the base state. So everything that's used for a qubit always has these 0, 1 base states. I'm sure at some point in the future there'll be more, God knows what's going to happen with any of this. You can then, when everything in the entanglement is collapsed, it's then possible, if you've built a decent quantum processor, to read that using a classical computer and produce some kind of output rather. So, the problem with, I think, how to explain entanglement is it's the same. I have a stress boob for this. This is my really helpful functional quantum particle. So if you imagine you've got the spin on an electron, and you've got, this is me pointing to 1, and then if I'm down here, I'm pointing to 0, and superposition can exist in any space in between those 2 points. In entanglement, the same manipulation is applied on one particle as to another. So if I have one over here and I turn it upside down, I have another particle and it will also turn upside down. The clever bit comes in is when you set up these qubits, you set 1 so it's pointing over here, you point 1 so it's pointing over here, and when you do the upside down, they end up pointing different places, trust me on this, but through this exact same manipulation. So what a quantum computer actually does is you feed something in with all these qubits in a state, you apply a manipulation to all of the qubits, you apply the manipulation to every single qubit, the entanglement causes them all to experience correlated manipulations, losing myself here, so I bet you guys are lost, and then you get an output in the end. When you observe the output, they collapse. This particle now says, I'm a 1, this one says I'm a 0, and all the ones in between. And hopefully, if you've done a really clever quantum algorithm, you've got an answer to some kind of problem. And this is, I'll expand on it, I promise, it gets very weird. The problem with these qubits is that we have no way of controlling the process. We can only manipulate qubits at the beginning of a process and then observe it at the end. If we try and interact at any stage in between, they collapse. Either the data is meaningless because it's come out before a process is finished, or the world blows up and things like that. Just you can't look at it. Every time, as soon as you observe anything in superposition, it collapses into a reality. So it becomes either 0 or 1. It's no longer in this really helpful in-between state, so it's about as much use to you as a classical computer. Do I need to apologise to my laptop all the way through this? Yes, so it's called maintaining coherence between qubits when they have this link, and they're all kind of tied up together in a weird little processor, and you feed all this stuff in, and you get really happy stuff out. Although how you'd even go about writing a quantum algorithm is completely beyond me. Right, so this is actually an artist's impression of a quantum computer, looking very drastic. I do think physicists like to make these things deliberately dramatic, but maybe that's just me. So what, as they've been actually building these quantum processors, they've started adding more and more qubits. Obviously, the more qubits you have, the more processing power you have, the more complex problems you can solve. So the race has kind of been, Google, I can do 10, and IBM's like, well, I can do 11, and they've been having this little race for the last 15 odd years, having a lovely time, flipping off at each other and all that jazz. But the challenge is to entangle them, set them all up in such a way that is useful, feed in some kind of algorithm, some kind of input, and then also be able to read that output on the other side, because you've got this weird unknown going on in the middle, and you've got to somehow harness this. You know what it's doing and how things will interact with each other, but there is nothing that can operate as fast. Like, obviously the reason we're getting these to do these computations is because we can't work them out ourselves. We can't check that they're right. We need something like this to check that itself is right. So it gets very very overcomplicated and very, very stressful. Right, so I'm going to dive back in, because I know I've hit you with quite a lot. I'm going to kind of take some of it back to try and make this, one, make it make a bit more sense, and two, also share kind of what makes qubits so amazing and why this is a little bit mind-blowing and everyone should be running around saying that Harry Potter is real. He is real, and I just didn't get the letter. As some of you probably know, light behaves as both a particle and a wave. So it is actually made up of particles called photons, but those photons flow and behave as a wave, and as such display some properties that waves have. So my pretty lovely ripple picture is to show you interference. So you get two peaks, you get a higher peak, you get two troughs, you get a lower trough, you get a peak and a trough, they cancel each other out. And this happens with light. So you've got constructive interference creating these high waves, you've got destructive interference taking these things away, and this is just a baseline to say waves are a thing, and they do these things, and it makes pretty pictures. Right, so this is a inference pattern from photons. So there are quite a lot of experiments that have been done. We have two, so if we go back to this picture, so here you've got the water coming through, but you've got two gaps here. Water is being pushed on a straight line, but when they hit the gaps, you get these ripples coming out from the gaps, and as these interact, you've got all your inference going on. So what I'm imagining here is my little electric gun, and I'm pointing it, and I'm putting all these particles through, and the light goes through and behaves and forms a pattern in the same way that the water does. So this is what you get. on the other side. Pretty, nicey. Probably isn't green in real life. Right, so this is my little electron beam gun with 2 slits, my little pattern. So this is introducing the single particle double slit experiment. Very nice and easy to say. Glad that they haven't invented an acronym for this. So you're firing these photons at the 2 gaps, and got ahead of myself a little bit. Right, so when you fire multiple electrons and multiple photons, it's behaving as a wave, and you get these inference patterns. So what they decided they wanted to do is to understand how these inference patterns were being formed. So what they did was they started firing one at a time, because they were like, well, these particles obviously know where each other are going. They must be interacting in some way, interfering with each other. How does it decide which gap it's going to go through? How does it know where it's going to land in such a nice pattern? Obviously, if we do one at a time, nothing will happen because there's nothing for it to interfere with. You've just got one wave lapping all on its own. It's not going to create anything on the other side. Then they were stunned because they still got an inference pattern on the other side of these gaps. So if you think you've got one particle, they've shot it through, they've let it land wherever it's going to land, and then they're just doing that at a really slow rate. So none of these particles have a chance to interact with each other and overlap. So why is it creating ripples? There's nothing for it to interact with. It's all on its own. A photon cannot be broken down any further than it already is. So is it splitting up? Is it going through both holes at once? Why is it forming a pattern when there's nothing for it to form a pattern with? Does it somehow know where the other particles are? Is there some kind of relationship between these particles? And that's when they started to look a little further. So all the physicists are really confused. The cat's confused because it definitely survived. And they really, really wanted to know what gap these photons were going through. They're like, I want to know what the probability is, where the decision is made, what happens. So they started putting little trackers on the inside of these slits, and they were like, oh, we're going to see, where does photon A go, where does photon B go? Every time you watch a particle land, it stops creating a pattern. And they were like, oh, okay, I've only watched it. Why is a pattern not forming anymore? We must have done something, we must have interfered with it, we must have moved it, must have thrown off its little bond with all the other particles. So they kept trying different things, and they were like, it's still not, every time we watch it, it's not forming a pattern. They started firing 2 at once, or they'd have 2 quantum bits that were entangled. Every single one that you don't observe forms a really pretty pattern. Every single one that you do observe just lands as if it stops exhibiting wave behaviour. It exhibits the behaviour of a particle. It just lands randomly as globules, as a normal particle would. No signs of interference, but the only difference is that it's being watched. Madness. Scientists say that this is magic, not science. Something else is happening. So instead, when their journey is observed, the photons just land in these clumps. And I'm thinking, well, the physicists are doing something really stupid at this point. And they've done quite a lot of experiments after the fact. And I wanted to ask you guys, what would you do next? How would you observe these photons? Where would you put the detectors? What do you think they should have tried? Because they're obviously, it must be them that's interfering with it, it must be them that's ruining the pattern. What would you do? Where would you put the detector?
Leave the detector there and unplug it.
Unplug it. Walk away. This is too complicated. I'm over it. It doesn't make
Do
sense.
you know what happens if you do that? You get the wave patterns back.
Every time you don't watch, it's behind your
Yeah,
back.
even though you've unplugged the cable 20 feet away.
It's honestly like electrons and photons actually have little personalities. They're like, well, I'm not doing it while you're watching. I'm not a performing monkey. Don't ask me to do these things. I do these things in my own time. Stop pressuring me. But what about, so how else would you think you could measure it? Like, where would you put? So at first they were looking directly on the slots. Would you move them back? Do you think that it was fine when they observed half of them? Spoiler alert, it wasn't! Alright, so every single time you watch it, every single time there's any way you could even infer which slot that photon has gone through, it refuses to form that pattern. Even if it's not, you're not looking at that direct particle, so you've got two twin particles entangled. They're firing both of them. One they don't measure, one they measure. Even though this is the only one you're observing, the one that's entangled still doesn't form an inference pattern. It's going, I'm not an idiot, I know that you can see me, I know which hole I went through. I keep telling you I'm not a performing monkey, I don't know why you're not listening to me. Has a bit of a teenage meltdown. And this is just bizarre and honestly has yet to have been worked out, which is great.
So Katie, just get my head around this.
Ta-da!
So the observation they're making is them with their physical eyes looking at
So it'll
something that
be
is
with-
left behind.
Not eyes, detectors,
Okay.
but it's impossible to say whether it's the observation. Like it seems that it's the observation, but the understanding is so lacking that they can't say for sure that is what's doing it. Because there's other things that you have to then start thinking about, like is it somehow connected to me? Like have I got particles that are somehow entangled with these particles?
What's interfering?
Do I have a field of Harry Potter magic? You tell I started reading it again. That's interacting with these particles. So it's kind of like observation. Like when you hear people talk about it, they'll say observation changes the results, but it doesn't necessarily mean that is it. They just don't really know.
So it's no human interference or bias or anything like that at all involved.
They don't think so.
Okay.
They
So
don't
they
think
could
so.
be. Okay.
Yeah, no, they've done multiple experiments and just can't seem to produce anything other than if they measure it, observe it in any way, if they somehow know where it is, won't produce a pattern. They don't think it's probably some lad called Kevin like kicking it and breaking it every time, but we'll never know.
If we've observed it, how can we tell that there is a pattern? Because that's observing it as well, isn't it?
So
It's
that's
the pattern.
yeah, no, that's a good point. And I didn't explain that fully. So the pattern at the end is like when reality has collapsed, it already knows where it is. It's only if you observe it at any point on its journey, still in superposition, that's when you're gonna break the pattern. If you're just viewing the output, reality's collapsed, that's okay, it's settled. It's like, it's okay, I know you've seen me now, it's too late, I can't go back. Does that make sense?
Yes.
Nice. Magic! Duh. You can tell, we get excited. Right, so what they started saying about this is that until the state is collapsed, a particle is actually acting as if it's a distribution of probabilities of where it could be. So you've got these two waves coming through, and actually what it's interfering with is the probability of where it could be. So this particle could go through slot A, through slot B, and therefore because it could be going through either, it can interfere with itself, even though a photon can't be broken down any smaller than a photon. Makes no sense. Magic. Is it observation that causes the collapse? We're not sure. How can we find out what's going on and what causes these interactions to happen when as soon as we measure anything, as soon as we look at anything, it collapses. We don't know what's going on anymore. Physicists are kicking cats across the room, it's all one Pete Tong, they're leaving them in the boxes. Just absolute carnage. Yeah, but this is very much how quantum processes work. So you have something in the beginning, you have an input, you have your firing of electrodes, they go through their superposition, they've got their different states. You have these preset logic gates that perform manipulations, which you cannot look at any time. And then you have the output at the other end, which if you're really, really smart, is something that you can use to solve a problem. So, applications of quantum computing, because even though it's magic, hopefully it will do something useful as well. So as someone's already mentioned, decryption that was thought unbreakable can now be solved very, very quickly and very, very easily by quantum computers, which has made people quite scared. but it's also quite good for encryption. So a little bit of column A, a little bit of column B, we're just going to have to get a bit smarter. Also, problems such as factorization. So there's actually an algorithm called Shor's algorithm, which is a quantum algorithm which Shor designed before there was a quantum processor to test it on. And the first time he tested it, it worked. So this guy created an algorithm for something that was only conceptual, and then the first time he ran it, it worked. Has anyone ever had a better day than that guy? I'd have run around with a t-shirt going in your face for about 6 weeks. Don't know about you guys. Have mentioned I have a large ego, haven't I? So one of the things I mentioned about classical computing is that you're asking problems to be broken down into ones and zeros. Like there are random elements to many things in life. That's a very wistful statement. But breaking problems down to something so basic as ones and zeros can lose a lot of the complexity of a lot of problems. And what quantum has on that is it has these random elements. It has these like physical interactions that can mimic other things in the real world. So building some molecules, even quite simple molecular structures, can be very, very heavy on classical computers, because classical computers can't mimic the way that they fit together, whereas quantum computers, they're much closer to the way they behave, the way they interact, and it's a lot easier to build these things. And there's a lot of hope for design of drugs, for like all the big diseases, and there's always these things that come up and everyone gets excited about, but quantum is actually looking like it could really help in these fields. And that's why it's quite exciting that all the big tech giants are taking it seriously, it's starting to move on, and hopefully it can achieve like really big things like this for us. So Google. So they are taking it very seriously. Google, they have been for quite a long time as of IBM, but it's great that this isn't just theory anymore. Like for a long time, quantum computing was kind of thrown around. This could be a thing that could be really useful, be really powerful. This is happening now, and there are like professors who actually know a lot more about what they're talking about that have said if you could go back in time, it's like 1940s, and you looked at everyone, like there'd be a classical computer like in every so office. It wasn't very common. Whatever time that was, would you not go back and invest? And he said, that's where quantum computers are now. They're here. They've done a slow little ascent into being practical, being applicable to real world problems, and they're about to take off. And we need to take it really seriously and actually pay attention to this tech, because it's not just in theory world anymore. So they actually look really cool. Pretty impressive. Most of the equipment, and when you see pictures of quantum computers, it's not actually because qubits are cool, it's actually keeping the state of the qubits in this isolation from the world, and at very low temperatures, very high pressures, that kind of thing. There's a lot of different types of quantum computers, but honestly I got so confused trying to look up all of them, I was just like, well, I'm just going to show you a pretty picture and move on. So quantum supremacy. So has anyone seen about this in the news from Google and IBM this week? Right. So quantum supremacy is the demonstration that a programmable quantum device can solve a problem that classical computers can't. So it's a drastic word, supremacy, proving that quantum will solve problems that we cannot with our current classical computers. Proving they're better, proving they're king of the land. Classical computers be damned. And this is a very pretty picture. So Google basically published to their blog and said, we have our 54 qubit processor called Sycamore, and they ran an algorithm on it and solved a problem. It was actually the flipping of, I'll put it on the side. So they asked it to randomise the flipping of 53 loaded coins. They'd either have heads or tails, but they wouldn't have a 50-50 probability. They then asked Sycamore to work out what is the probability of flipping these 53 loaded coins. And the amount of, quadrillion different ways for it to land. So for it to work out the probability of such a huge number of permutations is absolutely huge. And they basically said, IBM supercomputer, biggest supercomputer in the world, will take 10,000 years to do this for a ridiculous amount of time, and we can do it in 200 seconds, which is an obscene amount of reduction of time. So what does this mean? So this is quite an important and bold claim, and it's obviously grabbed a lot of attention. Maybe this is time that investment's going to start pouring in even more, people are going to take this more seriously, and obviously it's getting into mainstream media. It's quite exciting. This was followed the day after on IBM's blog, and I put this up just because I found it really funny that they put it in quotation marks, quantum supremacy, because they're basically saying that Google's claim is false. Quantum supremacy hasn't actually been proved. And I just felt that they got really passive aggressive when they did that, and it made me really happy. Maybe it's just me, I'm not sure. Right, so IBM basically fired back and said this is, well done for doing this in 200 seconds, but actually you said it would take us 10,000 years, and we reckon that Summit can do it in 2.5 days actually. Thank you very much, bit rude of you. It took us ages to build that supercomputer. There's a lot of reason for them to be pretty annoyed with Google right now. They're not very far behind. They have their own 53 qubit computer, so only one less than Google. I imagine them fighting over that. And the actual, the more in-depth explanation of quantum supremacy is there's a bit of a time band on it. So the fact that it was 10,000 years, 200 seconds was undeniable quantum supremacy. We've definitely done it. The fact that they're now saying that classical computers can do it in 2.5 days leaves a bit of leeway for what if we thought of a better classical algorithm. You cannot say for sure that we cannot do this as fast as you. You're just saying that you can't construct a classical algorithm that does it as fast as you can on a quantum. It adds ambiguity into it, and IBM are using that to lever it in and say, you lied, Google, you over-sensationalise everything. That was it on that. So, when are we going to see this in our own lives? What will quantum computing bring to us in our day-to-day computing? So, I love that I've done this as this is not going to happen, as if I know. Obviously, I don't know this, but it's highly unlikely that quantum processors are going to be in anything like your phones, like your laptops, that kind of thing, because the only reason that quantum computers perform better than classical computers is because of the granular parallelization, the fact that they can store these different states. They've got 4 instead of 2, they've got all these many things going on, and they'll never be able to be faster at most of the things that we use our day-to-day computers for. So it's not a replacement. What's much more likely to happen is that you've got these big companies that have their quantum processors, and companies will pay to run very computation-heavy algorithms on those, and you can actually already log into IBM's website and run a little manipulation on a real quantum processor, which is really, really fun and makes you feel really important for 5 seconds. But it's not going to be a replacement. It's a solution to new problems, and it's going to be infinitely powerful. But it's another step up. It's not a replacement, if that makes sense. Cool. So Google claims were very well and good, but the problem that Sycamore was asked to solve was pretty much what is the most quantum-focused problem we could ever think of. It's you've got a coin, it's got 2 states, you don't know which state is in the middle. It was designed to be modelled on something like a qubit. It's just unfair. It's like pitching a long distance and a sprint runner against each other. Whichever one of their events they pick, that one's going to win. It's just not a fair race. You can't come out and say this athlete is better because he can't compete against someone that isn't in his field. So, I spoke at you for ages. How are you feeling? Quantum. I thought a dog would help. It helped me. So in summary, qubits enable these parallel operations to happen at once. So at a granular level, so you've got classical parallelization, and then you've got this parallel bit parallelization. They're also extremely fragile, which is one of the other reasons you won't see it in your day-to-day devices, because they've got to be kept like stupid temperatures, stupid pressures, very enclosed environments. But there's so much future to be seeing for applications, for the chemical modelling, new designs. It's going to blow things apart, and the fact that we haven't even completely understood how everything works makes this so much more exciting. And I hope there's elements to this that do intrigue you because it doesn't make sense, because that's why I like it. Cool. I think you get a little bit of a break from me, and then unless you want to ask questions now, it's up to you guys.
What's the significance of one more qubit? Is that, am I right in thinking that will square the
It's to the power of.
Yeah, will it add another square on computational power? So is that a huge deal, or is it just 4 extra bits?
I'm sure it's not a square on top, it's 2 to the n. So instead of classical computing n states, it's 2 to the n. So if you've got 2 classical bits, you've got 4 states. If you've got 2 classical qubits, you have 16 states, she says.
So it's a significant jump.
It's a significant jump, exponential. Every time you add a bit, it's an exponential jump in computer processing power. Which is why 53 is actually an obscene amount, even though it doesn't seem very many.
Could you talk a little bit about quantum resistant algorithms? We'll go back to the security question, because that was... Well, obviously we've got, it's going to, when you can do all these calculations very, very quickly, a lot of cryptography falls apart. So there must be, I've heard about algorithms that are resistant to quantum computing cracking.
I have also heard.
Dangerous, I'm like,
that is an extremely interesting topic, and
Yeah.
I have also heard a bit about that. I definitely do not feel confident
Okay.
enough that I could give you a satisfactory answer. I'm very sorry.
okay, no worries.
But yeah, the only way, it's not like you have to fight fire
But
with
it's
fire.
hopeless,
You don't have to fight quantum with quantum. It's not infallible,
Yeah.
and it does work in a very specific way. So if you can design encryption that it just can't be worked around by the advantage that quantum computers have, then absolutely.
Yeah.
Maybe that's better than having a quantum computer fight, but I'd quite like a quantum computer fight, wouldn't you?
There's an encryption called one-time pad, which
Okay.
apparently is unbreakable,
Right.
even by quantum.
I'd like to sort of understand why. You know, it's
I can't.
yeah, exactly.
I'll tell you what one-time pad is.
Yeah.
One-time pad is basically, I'll give you a title of a book, let's say, is it Tale of Two Cities, Charles Dickens? Right, now my message is the 3rd word on page 1, 4th word on page 2, and 5th word on page 3.
Okay.
Right?
Yeah.
Now, that's fine. Nobody will understand, nobody will be able to crack that. The only way of cracking it is to have a copy of the book. And that's the one-time pad that we share.
Ah, okay.
Now, back in
That's
Church,
school.
Churchill's, yes, Churchill's day of the war, to communicate with America,
Mm.
what they did was they sent a record of random noise, copied it, and sent a copy to the States.
Right.
Added the random noise to the phone call, so it just sounded like random noise.
Okay.
And then, because they had an identical copy in the States that you could keep in synchronization, they subtracted it again and got the original voice back.
That's great.
But it's not crackable because it's a one-time pad, namely that disk.
Yeah.
Now, spies going to Germany had to memorise, typically a poem,
Mm.
and use that as their one-time pad.
Right.
And they use that to encode their message and then put it into Morse.
Yeah.
The other thing with one time pad is you can only use it once, so,
Yeah.
so once you've used it, you throw it away and use another
Yeah,
one.
you use the next bit.
Yeah,
Wow.
What a waste of books.
yeah.
What a waste of food!
It's so sad. I'm hurting inside.
You can read them while you're encrypting.
Oh yeah. Just like, could you send a better read next time? I wasn't really satisfied with that ending. Great code. Absolutely terrible character development.
But with this security, I thought that it applied only to initial state of the encryption. when we negotiating the key with if-held algorithm or with RSA that we can break this because it's just the problem of factorization of the numbers. But when we talk about AES encryption, I thought like it should not be possible to break with quantum
Yeah, but don't
computers.
forget the keys are negotiated
Yeah,
beforehand.
tricky.
That's the bit you can break. And if you don't break that, certainly on things like Wi-Fi, what you can do is you put a glitch in it and it renegotiates the key. So you can keep it renegotiating the key, so you've got lots of chances of analysing that encryption, which is the way you break Wi-Fi. I didn't say that.
Why is it in terms of the investments from the government? Why it's so little? It's only 94 million.
So it depends on the government. So the Chinese government have gone absolutely mental on quantum,
Yeah,
especially sort of things around encryption.
yeah.
So I think ours just don't care as much.
And also, so why didn't you go over to in terms of sharing of information? We talked about Google and IBM. I was also very interested in China, also very interested in America, because what they're pumping a billion over there.
Yeah.
Whereas, I don't know, 94 million shares with Sussex, Oxford, Cambridge. I don't know if that would be enough for this country to.
There's a lot.
forward.
I focused on Google and IBM's quantum computers purely because they're easy to find things out about. They're certainly not the only ones that are getting to this level of advancement. And you're right, there are other players in the game that deserve proper consideration as well. And if China's going to start making more powerful ones than us, we're probably going to want to catch up with that.
Because of your interest in it, have you thought about linking up then with others in China, with others in Russia? I know that you're working over the first egg, but do you know about any like alliances being made?
I don't know anything about the politics of it, I'm afraid. I'm more of a science is awesome kind of girl rather than getting involved in the arguments and the country issues, especially when it comes to encryption. Obviously, we'll never know how advanced China has got with their decryption because they'd never tell us. They could be able to see everything now, we have absolutely no idea. So it's a bit scary, but no, personally, not at this time.
I mentioned that because, like you said, an example, we're in 1940s, so why wouldn't you want to put an investment in that? And I say that because in officer interviews, they're talking about quantum and bringing China up, and they're bringing the fact that China is sending whatever they're sending into space. So they aren't in 1940. We are. And it's all a very bit scary, to say the least.
Yeah, I think personally for me, the fact that I am inside it and that I'm not then personally involved is that if I was to be involved, I'd want to be one of the people making one of the processes. I'd want to be right on the forefront of it. It wouldn't be enough for me to be one of the middlemen. And I could retrain what I do, but it would take quite a lot of time for me to get there.
So how do we make it sexy then for the next generations coming up?
How is that not sexy? That's the sexiest thing I've ever seen!
Sorry.
Inverse patterns!
Yeah.
What else do you mean?
It totally is.
They disappear when you let them! That's like half the people on Tinder.
You're right. You're right. Definitely.
I do think it's trickling down more into mainstream media. The Daily Mail had something to say about it. Probably wrong, not biased. But it did have something to say about it, and it's nice that the thing is, when even the top physicists don't really know what's going on, everyone has a good idea. Like, you can ask anyone what they think, and that's one of the reasons I would be like, how would you what would you have done next to try and work out whether it was observation? Because no one's figured it out yet. That's up for grabs. Like, someone can do that, and someone will do that, and it will be amazing. And I hope it's me, but I might have to put a bit more effort in. Yeah, no, I think it's already sexy. Maybe just even more artist impressions of overcomplicated quantum computers and people running around giving talks with dogs and cats in.
I really do hope you go ahead with it and go over to the various colleges in West Sussex and speak about this, because we have some young physicists coming up that would definitely be interested. Yeah, and we need all of them. We do.
Well, always happy to spread a little love for quantum computing. So, as you may have noticed.
Any last questions?
Yeah, I've just got one question. I'm curious, a little bit curious about the nitty-gritty of exactly how you get this information out of the black box. I sort of get that you're looking at the probabilistic and stochastic states of these particles, but I'm curious because I'm assuming that you still need a classical computing algorithm to make sense of this at the end. So I'm a little bit interested in that interface between the quantum and the classical.
So the interface is only ever between the collapsed state and the classical, which, because it's two states and one's a zero, makes a lot more sense as an interface. There's never any interface between classical and anything in superposition, because it would fall into collapse.
Right.
I feel like that was a bad answer to your question.
So you're essentially doing calculations on the probabilistic states, yeah? Why can't that be modelled, in a sense, without those particles in themselves as a simulation?
So as why can you not simulate the behaviour of qubits on classical bits?
You can. The problem is it's slow, because you're back down to the constraints of classical computing. Every operation of a qubit is not actually faster than a classical bit. It cannot switch faster than a classical bit can. The power comes because each operation is a compound operation. Every change on one of the particles is a change on all of the entangled particles. You're doing all of these instantaneous changes at once instead of 0 to 1, 0 to 1. It's just not parallelization in the same way. You've got like 4 parallel processes, or you've got every single bit switching at once, and that's where the exponential power comes from. So yes, I would agree that you can model it, but it is too slow.
So essentially, if you're getting a mechanical result, you're putting it in the classic way and you're getting it out the classic way. The black box is essentially something that just speeds up the process by an infinite degree. It doesn't change in any way the way that you're looking at and inputting the data in that classical sense. It's just really fast.
Yes,
so
not to a point so far.
It doesn't. I'm just like interested in the idea
whether
we can
really
approach the whole of the paradigm of computing and the way that we interact with computers and the input and the output state as a quantum paradigm in itself. I imagine like something like artificial intelligence would be really useful to use quantum computing in, because there are models with certain advanced forms of thinking about consciousness as being a quantum behaviour. Like Penrose's work with
This is where we're kind of limited at the moment, though, because we have to be using classical computers either side of this quantum computing,
kind of like a bit
and
of a
we're
pipeline
absolutely certainly losing a lot of the power that's involved in these qubits because we can't directly read them or interact with them. But that just might be a limit on us. So until we find some bigger, better aliens, we might be limited for a while. I'm rooting for the dogs to sort this one out, to be honest. But we'll see how that goes.
Thank you.
Thank you.